Hello. Hi. So now John and Christian will talk about Ceph. So the stage is yours.
All right. Thank you very much. Good afternoon, everybody, and welcome to our talk on distributed file storage and multi-tenant clouds using CephFS. My name is Christian Schwede. I'm working as a software engineer at Red Hat, obviously, and with me is...
Hello, my name is John Spray. I'm also an engineer at Red Hat. I'm the former maintainer of CephFS and the current maintainer of the Ceph Manager daemon.
All right. So, in this presentation, we want to give you a brief overview about the key components that we're using to expose actually shared file systems within an OpenStack cloud. We're going to introduce you to OpenStack Manila, and we will continue, or John will continue, with the CephFS native driver implementation. Next will be some information about the NFS Ganesha driver, which is used lately and has some improvements about the native, or using the native CephFS driver directly. And at the end of the talk, we are going to give you an outlook on the future work that is happening right now with the upcoming OpenStack Queens release and beyond the Queens release. So before we talk about the components that we are using, let's quickly recapitulate what's the challenge that we actually try to solve here. So what we want to do is we want to enable tenants or administrators of virtual machines to expose or to use a shared file system across their virtual machines. At the same time, we want this shared file system to be tenant aware, meaning that we don't have like a single global shared file system for all the machines running there, but only to a subset of the machines, and another subset of machines from a different tenant are not able to access, of course, data from the tenant A, for example. The whole deployment should be self-managed, meaning that the tenant administrator from tenant A, for example, can set up, create shares, delete shares for their users and their virtual machines. And the operator of the underlying OpenStack cloud and the storage backends don't need to interact directly or need to set up the different file systems for their administrators. As an operator of this cloud, I want to be able to reuse my hopefully I want to be able to reuse my actually available storage backend system. So, for example, if I have already Ceph running that exposes block storage, I don't want to add another software-defined storage. I want to reuse this existing storage for my shared file systems. So how do we solve that? Actually, we're using 3 different projects to solve this issue or this challenge. First, we have OpenStack Manila. OpenStack Manila is a OpenStack shared file system service. We're going to use Ceph as the software-defined storage solution, backing up your OpenStack cloud. And we're going to use NFS Ganesha, which is a freely available NFS server implementation. So let's have a look at OpenStack Manila. The OpenStack Manila is the OpenStack shared file system service. It actually exposes a bunch of, one API that your users and administrators of virtual machines can actually use to request of shared file system shares, delete shares, create new shares, stuff like that. So as a tenant administrator that want to use a shared file system, you send a request to the Manila API. And the Manila API in the background, there's a second service called the Manila Share Service, which actually talks directly to your storage cluster. And the storage cluster then exposes, for example, an IP address where you can mount this shared file system. And at the end of this, the tenant administrator will get back an address, an IP address, for example, that you can use then in your guest VM to actually mount this created share. And finally, your guest VM is talking directly to the storage backend. Now, there's support existing within Manila for different backend drivers, quite a few proprietary drivers that are well supported by their vendors. There are some generic drivers for open source implementations, but until the addition of CephFS, there was no real production-ready open source driver available, meaning, for example, that you have stuff like highly availability services running there. So CephFS added this features And with CephFS, it's now possible to run really a production load using OpenStack Manila with a completely open source cloud deployment, OpenStack deployment. So CephFS is actually a distributed POSIX file system that is built on top of Liberados and Rados, the technology that actually makes Ceph or is Ceph. Ceph itself is probably also already well known, for example, for its block storage service using Rados block devices. Rados block devices are often used together with OpenStack Cinder to expose volumes for your virtual machines running on OpenStack. And it also exposes object services called using the Rados gateway, RGW, exposing an S3 and object and Swift compatible API implementation. So the OpenStack Foundation is actually doing surveys twice a year, typically before the OpenStack summits. And it turned out that most people, more than 50% of the operators, actually want to use CephFS as their backend for their Manila service. And there's a good reason for this. As I mentioned early on, most of the times when you have already a Ceph cluster running Cinder, you might want to reuse this one, right? You want to use only a single software-defined storage within your cloud. And this drives actually the demand to use CephFS within Manila. So before John is taking over and giving you a more detailed view on CephFS itself, I want to explain a few key terms that we are using during this presentation. When we actually deploy OpenStack clouds within Red Hat or for our customers at Red Hat, we're using a concept, or we're using a tool called OOO. OOO actually means OpenStack on OpenStack. And we have a so-called undercloud, which is basically a management node, and this management nodes then deploys in so-called overcloud. And this overcloud is shown here, for example. We have a bunch of controller nodes that, for example, expose API services, not only Manila, but let's say Keystone as well, the Nova API, and so on and so forth. The controller nodes are also running a distributed MariaDB cluster and other services as well. Of course, we have some compute nodes where your virtual machines are running on later on, and we have some storage nodes. We are exposing or setting up actually a few different networks by deploying an overcloud. And we have public networks that, for example, expose the API services to the users. This is also called a control plane. And we have some private networks that we're using, for example, for the storage traffic in the background. And these are typically called data plane networks, and are private and normally not seen by, for example, or shouldn't be seen by the guest VMs, actually. All right. That's that. I think John is going to tell you a little bit more about CephFS. Oh, sorry.
So the native driver for Manila is the simplest thing that we have at the moment. It's been in OpenStack for a while now, and it acts as the basis for what's coming in future releases. When we say native in this context, we mean very good performance, because all of the guest VMs can talk to all of the OSDs in the Ceph cluster. That gives them a scale-out level of bandwidth. That means they're only limited by the bandwidth of their own network interface. So if you want to get 10 gigabits or 40 gigabits or whatever of storage into a virtual machine in an OpenStack cloud, this is a way you can do it. It's fairly simple to deploy from the point of view of the person deploying the cloud itself, because you're not deploying any extra protocol gateways or anything like that. If you're running OpenStack on a fully open source platform, the chances are you already have a Ceph cluster that you're using for RBD images via Cinder. So you can use the same underlying Ceph cluster with a single large CephFS file system and expose that as Manila volumes. The way we implement the concept of a Manila volume in the CephFS native driver is simply as a directory. So CephFS goes a little bit further than what's required by POSIX in terms of what it provides you. It gives you per subdirectory quotas and per subdirectory usage data that lets you do an impression of a particular directory being its own file system. So when you type df on one of these subtree mounts, you're getting that per subtree usage information, and the quota is being enforced at that level, so that when somebody asks for a 10 gigabyte Manila volume, what we're really giving them is a directory with a 10 gigabyte quota. There's a link there to a presentation from CERN, who are using this driver at some scale already. So here's the network diagram. And the important part of this is the red section at the top, where we have the Ceph storage network that's connected to all of the backing storage servers, the OSDs, which typically would be separate from the networks that you exposed to your client workloads. And the reason for that is that Ceph it has some security built in. It does have its own crypto and authentication and so on. But that's not designed for use in public. It's not the kind of thing you would expose directly to the internet. And it's not the kind of thing you would usually expose to untrusted client workloads that somebody brought to you and asked to run your cloud. So tenant A and tenant B here are just both connected to the same network, so they can potentially interfere with each other somewhat, and they can certainly run the risk of interfering with the underlying Ceph cluster. The upshot of that is that you would only use the Ceph native driver if you trust your workloads. And that is the case for quite a lot of OpenStack users, as it turns out. To begin with, I expected this driver to have very little uptake because it has this drawback. But we've had a bunch of people using it because it turns out a lot of people using OpenStack are just using it as a way to automate their infrastructure for their own workloads. And for those people, the security caveat is acceptable. So to recap, the pros here are the performance. It's shown itself to be popular with users. The implementation is very simple. It's just a directory that somebody's mounting. And I didn't mention HA, but that's because there's nothing to it. The Ceph cluster already provides high availability in itself. There's no extra effort needed to make this solution HA when it's used by Manila clients in an OpenStack environment. And the downside, to emphasize again, is that we are giving user VMs direct access to the storage network, which is certainly not a best practice and is only acceptable if you can justify it based on how much you trust your applications. The other slight downside is that the clients running inside the Nova VMs need the Ceph software installed to mount the Ceph file system. So the Ceph client is in the Linux kernel. So this isn't massively onerous, but it means that when you deploy your clients, if there's a new version of Ceph coming out, you need to worry about things happening inside your Nova VMs. So again, only works if you have a very good relationship with whoever is running your applications and whoever is building those VMs. So having talked about what's wrong with the native driver, I'll pass back to Christian for the current work.
All right, thanks, John. So because of these drawbacks, the engineers were actually looking into a different way how to expose the shared file systems to the users. And what has been implemented is actually an NFS-backed service that exposes or that actually uses a CephFS and a CephFS driver and exposes the shared file systems to the guest VMs using NFS services. This will be completely integrated with the upcoming OpenStack Queens release, which is coming out in a few weeks. And I'm giving you a little bit more detail how this works. So first of all, we're using NFS Ganesha. Ganesha is a user space NFS server supporting multiple NFS versions and built on using a very modular architecture, using pluggable file system abstraction layers. And these file system abstraction layers already include different open source file shares, for example, ClusterFS, GPFS, Lustre, and CephFS. Ganesha makes it possible to actually dynamically export and update the configuration without actually restarting the service itself. So when you add a new share to the Ganesha server, you don't need to restart it. You just send a signal using the dbus protocol, and it will update and export the new service, for example. It has also some metadata cache implemented and included. So when you're using NFS to access a shared file system, not all your requests need to go to the underlying storage backend, but some of them are already cached. So how does it look like when you want to use the CephFS NFS implementation? Your tenant is, for example, using the Horizon web interface or the Manila command line interface and sending a request to the Manila API service. The Manila API service is then talking directly and natively first to the storage cluster running CephFS and returning a directory path. Next, the Manila service will update and send the information to the NFS Ganesha gateway, which itself mounts this directory path locally and exposes the NFS service using the NFS protocol itself. So at the end of the day, the administrator has an IP address with an NFS service that you can mount on your guest VMs. Now, this is all happening on the control plane. Let's have a look at the data plane. So on the data plane, it looks now a little bit different because your clients are no longer talking directly to the CephFS daemons or the Ceph daemons, but only talking to the Ganesha NFS gateway. This has some benefits, of course, because we can better isolate traffic from each other, and as John mentioned, the drawbacks that we have when using CephFS directly are no longer come into play here. But it adds actually, well, a kind of man in the middle here in the data path. So you really need to run the Ganesha service in an HA mode, a highly available mode, otherwise it would become a single point of failure. So what we're doing here when we set up an OpenStack deployment using OOO, we're running Pacemaker to enable or to run Ganesha in an active passive mode. If we look at again at the network level, we now create a new network just for the NFS traffic itself. And the tenants are no longer directly connecting to the Ceph network, but to this NFS network. And Ganesha is also connected to this NFS network. So you might wonder actually if both tenants use the same NFS network to access the data services, you might see traffic from each other. Well, Manila actually triggers or creates OpenStack neutron security rules to isolate traffic between the different tenants from each other. As I mentioned, we are running Pacemaker on the controller nodes within our OOO deployed environment. So there's a concept within OOO called composable roles. And composable roles actually make it possible that you, for example, define a set of nodes that are running specific services. And it would be a nice idea to actually run a few standalone nodes just for the Ganesha services and with their own Pacemaker cluster. However, the Pacemaker cluster at the moment is tied to the controller nodes because it's also controlling other services as well. So we can't easily remove or move the Pacemaker service to a different node. So Pacemaker needs to run on the controller nodes, and because of that, Ganesha itself needs to run on the controller nodes. And, for example, needs to restart the Ganesha container. Ganesha is running containerized in newer releases within OpenStack within OOO. Needs to restart it on a different node. So to summarize, what are the benefits using the CephFS NFS driver implementation? We have better security because we can actually isolate the user virtual machines from the Ceph network and its daemons. We already have familiar NFS semantics that are included in most guest operating systems, which is for some guests or for some operators pretty important because you can't, for example, add Ceph drivers to your, let's say, proprietary guest system. But instead, NFS itself is widely supported already out of the box. We have some path separation in the backend storage system, and by using OpenStack neutron network policies, we can actually enable or enforce that the backend traffic is isolated from tenant to tenant. And that gives us the possibility to run it more in a public cloud environment compared to, for example, a private cloud deployment where you can trust your virtual machines. But there are also some drawbacks here. So as I mentioned, Ganesha is a man in the middle now in the data path, and your guests are no longer directly to the HA-enabled or HA-ready Ceph cluster, but only to the Ganesha service. So what we would like to do is actually, we would like to run, best would be to run Ganesha in an active-active mode, or run, for example, Ganesha in a way that we spawn a separate Ganesha instance for every tenant. So instead of setting up a single Ganesha service when we deploy the OpenStack cloud, we could actually start a Ganesha service per tenant on demand, and by doing so, we would increase the performance that we get out of this total service and are not exposing like a single point of failure because you only have a single Ganesha service running. And with that said, I'm giving over to John again, who's giving you an outlook on what comes next.
So it's fairly clear that we've got the native driver that gives you great performance and simplicity, but has a big security problem, and the NFS driver, which is much easier to use and much more generally applicable, but has some innate limitations in terms of performance. Naturally, we want to build a scale-out NFS solution. The way we want to do that is to have a tighter integration between Ceph and Ganesha. Pacemaker and CoreSync are very useful tools for HA up to a certain scale, but we envisage that in the future, we're going to have NFS daemons that need to scale out potentially as far as Ceph scales out, so potentially up to hundreds. And we'll also want to have Ganesha daemons that are created on a per tenant or per share basis. So we'll have a much larger volume of these than Pacemaker CoreSync will be able to handle. Ceph, fortunately, already has lots of general purpose bits for keeping its own services running. So we intend to put a wrapper around NFS Ganesha and run it in a way that it's slaved to the Ceph cluster. That should also make it simpler to deploy because there's no extra configuration to do for CoreSync Pacemaker. And also easier to use for users in general of Ceph. So whether you're running with Manila or any other environment, we can potentially give you a single command that both creates the file system and configures the scale-out NFS on top of it. Kubernetes comes in here as well. So there are a number of efforts ongoing at the moment to bring Ceph into Kubernetes environments, not only to provide the storage to applications running in those environments, but also to take advantage of what Kubernetes can do to run our services, to keep our services up, scale them, and so on. And that will apply to NFS Ganesha. So when Ceph wants to create a new Ganesha daemon, it will ask Kubernetes to do that for it, whether your application is based on Kubernetes or not. So even if you're on a traditional OpenStack cloud, you would still probably be using Kubernetes behind the scenes if you wanted a Ceph cluster that could provide this kind of capability for you. So here's a diagram of what that solution looks like. Manila is still there in the top left, and it's calling down to the MGR there is the Ceph manager daemon. It's one of the daemons in a Ceph cluster. And it asks the manager to create and delete shares for it. And on Manila's behalf, the manager calls out to the bottom there to Kubernetes and asks it to create these pods that contain a new service that we intend to create called NFS-GW, which is a sort of analog to RGW, the Rados gateway, but it's doing NFS. And those pods would be the data path for the user applications. You see Courier is mentioned in the bottom left of that diagram as well. That's about the network configuration that goes with this. So as well as creating NFS daemons per tenant, we will also need to be doing network configuration per tenant to give them the right level of isolation. That's very much an emerging area in Kubernetes. Traditionally, Kubernetes pods only had one IP, and that was all you got. But things are moving fairly quickly in Kubernetes, and we imagine that things like these storage containers will be a sort of early adopter of the new improved stuff that's going to be out there in Kubernetes. So this is the sort of third revision of that same basic diagram. But this time, you can see tenant A and tenant B are both talking to their own Ganesha. They're not sharing anything at all anymore. They're fully isolated, which is kind of what we wanted to begin with. So this isn't trivial, and it's not all just plumbing. Making a scale-out Ganesha cluster on top of CephFS has some challenges. Running it to begin with is very easy. You can download Ganesha and do this today. It's a shared file system. You can put multiple front ends in front of it, and that's all fine. But when a failover happens, we need a little bit more stuff happening here. So NFS clients have some state with their NFS server, but the NFS server is also a Ceph client. That creates a fair bit of complication in terms of what order you restart services in when a failover happens, but also at what points you have to put the NFS services into what they call grace. So when you put an NFS daemon into grace, it means that it's not going to let any clients take any new locks or access any new files until the failed daemon that we're currently replacing has come back. And that's to prevent locks getting stolen and provide the right semantics for the user application. It's quite an obscure aspect of implementing NFS that most people aren't familiar with, but it becomes very important once you start doing active NFS and scaling it out, especially when you're putting it on top of another system which is doing its own HA underneath, in this case Ceph. Even further out, MDSs in Ceph clusters, the metadata servers, are themselves a scale-out cluster. So we'll want to scale out the MDSs at the same time we scale out the MDS daemons to let you do things like small file workloads efficiently. NFS delegations will speed up these workloads a lot for certain applications that don't want to keep doing lots of round trips all the way down to the Ceph cluster. That allows so a delegation allows the Ceph cluster to say to the NFS daemons, okay, you manage this file for the moment. You don't have to ask me to do more accesses to it. PNFS, parallel NFS, everybody's been waiting years for PNFS. It might still happen one day. In the context of Ceph, what that might look like is us putting a little lightweight daemon in front of each of the OSDs that allows PNFS traffic to go through it. And what that would mean would be that an individual NFS client, even when going via NFS rather than the CephFS native protocol, would be able to get the full bandwidth of the cluster. And finally, there's the use of this outside of OpenStack. So Manila is a fairly separable thing from OpenStack. It will be interesting to see to what extent Manila gets reused in other environments. But also to what extent the components that we're building here to support Manila get wrapped up in other environments. So much of the same stuff that somebody wants in Manila, they'll also want in Kubernetes or any other container orchestrated environment. So we anticipate this stuff that we're building into Ceph and on Ceph for Manila showing up in other frameworks as well. That's all I've got. Thanks very much for your attention. Any questions? There's one over here.
Did you mention Kerberos at all in the NFS?
I did not. So you're asking about Kerberos, which I didn't mention, and that's because that's a general purpose NFS aspect, and it doesn't change if you're using Ceph. So that's... whatever Kerberos support exists in your NFS daemon will still exist when you're running it on Ceph. I'm not an expert on that aspect. This one here. So I think the question is, when I'm running NFS on top of CephFS, and both of them are doing sub-mounts, subdirectory mounts, how are we tracking the metadata beneath that? So the metadata inside Ceph is completely unchanged. You can mount the overall file system that's storing these volumes, and you will see all of the volumes as subdirectories. And you can even read and write to them safely at the same time, because our whole concept of a volume is this sort of sham, where really it's just a directory. We don't have to really make any changes at all in how the metadata is stored on the back end. Yes?
You plan to run NFS directly on Ceph and not on CephFS? On the last slide that you showed? Or you're still planning to
It's still on CephFS, yes. So, sorry, the question was... Yeah, sorry, I forgot to repeat the question there. It was, will the NFS daemons still run on CephFS, or will they run directly on Ceph or the underlying Rados? And the answer is it's still CephFS, just with a more nicely packaged NFS solution on top of it.
There was one question here.
Right. So the question is, why are we doing file systems and not block devices? It's for workloads that require a shared file system. So if you have a workload that requires storage which is only accessed by one VM at once, then a block device works well. But if you want a file system that will be accessed at the same time by many different nodes, then Manila is what you want. So Cinder is still great for single node access, and Manila is primarily for people who want shared file systems accessed by many nodes at once. One last question. I'm sorry, I can't hear you.
I'm sorry.
The question was, when deploying the Queen's version of all of this with the NFS solution, does it require any special dependencies or configuration, especially on the network side?
So within the Queen's release, it will be fully integrated on the OOO side. So when you deploy an overcloud using the Red Hat's OOO, then it will be fully integrated already. You just need to enable it during the deploy time. So when you're familiar with OOO, you have a bunch of environment files that, for example, set various items, networking, stuff like that. And with the Queen's release, it will be as simple as like just adding an additional included environment file, and that will spawn up and deploy the Ganesha services and other services, so you can just use it basically out of the box. That's the idea. Okay.
Okay, I think that's it. Thanks, everyone.